that
we can start.
oh,
For me,
okay.
we can start.
Taking in account that the reference public is general public and young students, in the sense that high school and middle school. Okay, so let's start with the title of your conference, 40 years journey. How was the situation of the black hole studies 40 years ago when you started?
Well, okay, I mean, the mathematical, theoretical idea that such objects might exist is 100 years old now. But there were severe doubts in the 1950s and early 60s that these objects, which, you know, basically constructs of a theory and in fact also fairly highly constrained symmetries, so spherical symmetry or an axisymmetric situation, where you then could imagine that the density would be so large of the mass that even photons cannot escape. That was considered to be potentially a breaker in the sense that nature might not have such a symmetry. And if not, well, then maybe these objects don't exist. So that was sort of the situation in the early 60s. Talking to one of the theorists who is one of the famous theorists in the field, Roy Kerr, who found the second famous solution of a spinning black hole. He basically said that in 63, I tell you about why that number is so important. In 63, say the astronomers and even the physicists wouldn't care about the relativists. There were different communities. They would not talk to each other. And that then changed within a year, because then these discoveries in X-ray astronomy on the one hand and the quasars on the other, all of a sudden produced objects where the likely interpretation was that of a remarkably accreting black hole, that is, a black hole which a lot of material goes into it and thereby produces energy on its way into the black hole. That all of a sudden became sort of a possibility, a theoretical likely possibility. But that's still different from knowing about it in the sense of empirical evidence. And so the empirical evidence then took another 15 years to develop into something which one could do. And there the issue which is important to understand is that these objects are very small. I mean, what you would call a black hole is extremely small. I mean, for the Earth to be a black hole, the thing is 1 centimeter. 1 centimeter size, entire mass of the Earth, that would be a black hole. For the Sun, it's 3 kilometers. For the objects which we call massive, supermassive black holes, it's sort of the size of the Sun to the size of the Earth orbit. Yeah? That's sort of the kind of very small compared to what you usually achieve. And so to get there, that's the challenge.
Okay, could you describe your results? Also, how big is the research group? What kind of telescope you used, and what are your results?
All right, so the object we are studying, in retrospect, what we now know is the nearest massive black hole. Why? Well, because massive black holes sit in the nuclei of galaxies, and the nearest galaxy is our own, so the nucleus of our own galaxy is the likely location of the nearest black hole. And that was suspected in the early 70s, and then that led over time to efforts to use the dynamics of what? Of particles, of gas, of then later stars, to measure motions and then infer from those motions what the mass distribution is. And then draw a conclusion, does this have to be, could it be a black hole? Initially it could, and then over time it got stronger.
How big was or is your research group, and what telescope you use?
Right. So the group in its entirety now I'm taking together the students, postdocs, scientists, and also the engineering staff, because we're building a lot of instrumentation, is 50 people. So it's a big group, very big group. And that is because we nowadays build very ambitious instrumentation. When we started, that same number would have been 5 or 8 or something like this. So we've grown a lot as the aspirations, the ambitions, and the difficulty of the work increased. We grew a lot. Now, how do we do this in which telescopes? Well, what you want to do is you want to measure very fine things. So you need angular resolution. That immediately tells you short wavelengths actually and big telescopes. And so that's what it has played to go to the wavelengths where we can see the center of our galaxy. That's not the optical, because there's so much foreground dust between us and the galactic center. It's the so-called near-infrared. And then big telescope nowadays means 10 meter class, 8 to 10 meter class telescopes. In the future will be even bigger, for 40 meter class telescopes. And we actually using the fact that one can combine the light from several. So, the biggest machines we can put our hands on, because that gives us the highest resolution.
Okay. And just quick, what is a black hole? It's not quick, but try.
Yeah. No, I think it's really rather simple. I mean, fundamentally, what is built into Einstein's theory is, number one, is that light is affected by masses. It's formulated in the sense that any mass, U2, I2, influence our environment by impressing a so-called curvature into the space-time. And other masses, I from you and you from me, notice that if we want to move, so to speak. If the mass is large enough, well, then we surely notice it, because it changes the way we can move. And the new thing in the theory is that is true also for photons or light. So photons see gravity, and Einstein became so famous instantaneously because he predicted the bending of the light by the sun when it was in front of a star field. And that was then experimentally during an eclipse checked out in 1919, and sure enough, the number which was measured was exactly what he had predicted. So that's why he's so famous. And if you think that is just a light ray, which from a distant star behind the sun, which grazes, so to speak, the surface of the sun, that's not much of a mass which you have there. So you put there, instead of a sun, you put there 4 million suns, then that light would not come to us. It would fall into the black hole. And that's the idea that light is affected, and if the mass is large enough and compact enough, then the light just cannot make it out anymore, and so then it is black in the sense of radiation.
Sì, no, è che davo lo stacco. At the beginning, there were some doubts of the existence of the black hole as a phenomenon. Now we have your result and the Event Horizon Telescope. The existence of the black holes, in the sense of Horizon and Event Horizon, is proven beyond any doubts, or there are still some alternative hypotheses that are still alive?
Yeah, well, okay. I mean, so you've left out one very important additional evidence, that's gravitational waves. So if you take the three together, I think we are at the level of where you would have to say, we don't see any way out. But there are theories which are close to that of general relativity, but not equal to that. So, in other words, you could write a theoretical ansatz which is somewhat like GR, with many of the same things in it, but more features. And such theories exist, and in principle, you would have to exclude, so to speak, every one of them if you really are serious about it. And there are some which currently still would survive. Put in terms of the ultimate what you want, is the statement by general relativity that if you have a mass and you turn that into a black hole, then you only need 3 numbers. Let's say 2. I forget about the electrical charge. 2 numbers. One is how quickly the object spins and the mass. Nothing else is needed, which is remarkable. I mean, it doesn't matter whether I construct a 4 million solar mass black hole, a 3 billion solar mass black hole, a 10 solar mass black. It doesn't matter whether I constructed any of these through the collapse of a star, whether I threw rocks into it or VWs. That does not matter. Only matters what the mass is and what the spin is. That's remarkable. These objects are truly simple. But that tells you immediately that there, ultimately, that's the way to test it. The simplicity. And there we have not, we are measuring the mass, we have excluded most every alternative scenario, but at least we cannot measure the spin quite yet. The gravitational wave people, on the other hand, they're close to that, to spin measurements, but they are looking at black holes which are specifically low mass black holes, okay, currently. So I would say we are on a good path. There's definitely more to do. In the end, there is one very fundamental question, or two. One is the so-called singularity. So the general relativity says if you go ahead and you know that over there is a black hole, then you take your truck and you bring in rocks and you throw the rocks in. And somebody else has another black hole, the same mass over on the left side there, see it, and throws, footballs in there. And the two of you do this for a little while so that the mass increases by a factor of 2. Then general relativity says, can't tell the difference, that one and that one is the same. And the quantum theory community would say absolutely not, because footballs and rocks have different quantum properties. So which one is right? And where is the answer? Where is the information which could tell you whether it was rocks and footballs? So that is, it's a bit of a, you could say, it's a highly scholastic discussion in a way. So you could say, I'm a practical person, I don't care. So that's what you could do, but mathematically you cannot. You should know. Do you need to know, so to speak, all these numbers? It's a huge string of numbers to know what the quantum numbers are in the black hole, or don't you care? And then the second one is the singularity, which means all of that energy and mass is in a point. Point means if the mass is very large, in a point means infinite density. And everyone in physics, me included, says it's not likely. And how do we solve that? Well, we need a theory which goes to that scale. We know that from quantum physics, right? I mean, the Greeks thought that atoms were undivisible, atomos, yeah? And then when we discovered the atoms, then we thought, okay, well, there's a nucleus, and then we thought the nucleus was a point, and then the electrons were points, and we all learned by having better machinery that this is not true, and then the theory had to be adapted to this. So this is where some of the future questions are.
Okay. And then what is, in your opinion, the next breakthrough that we can expect in the field of black holes? And if traditional astronomy has still a role in this breakthrough, in the future breakthrough?
Well, aren't you proud? Aren't we proud as a community that we have taken over from classical physics in studying what is perhaps the most fundamental issue in modern physics? Mm-hmm. I mean, there are physicists who are calling the black holes the atoms of the 21st century, right? So it's really fundamental what is there. So how far will we go? Well, one problem for sure is this stupid event horizon. Because, if you want to get down to this singularity issue and actually empirically test, is it or is it not true, yeah? Then you want to go into the event horizon, send something in there and get information back, and that is not possible. Mm-hmm. So that's a really a conundrum, which I don't know how we deal with that. The other one is how close can we come to the event horizon, and will there be quantum mist vapor, sort of coming out of this thing if you go close enough. I don't know, I can dream about it, but I can't tell you the answer.
Okay, yes, probably as a fact of our songs or songs of the songs. Or do you think that is a quick improvement?
No. I would say that the improvement over the last years, even though in my case 40 years for the gravitation wave, pretty much the same number. For the Event Horizon Telescope, it was also pretty much the same number because VLBI was also, developed in the 1960s. So I mean, it's all of these fields took 40 years from the fundamental development of the technique to applying it to this very tough problem and having success. And then you can ask what next. Well, I think the most definite and certain thing is that space gravitational wave interferometry will absolutely take the next step if it will work. Now that's much more likely a statement, but say 20 years ago when ESA was making, or 10 years ago even, when ESA was making decisions, many people wouldn't believe that space gravitational wave interferometry would be possible. Now perhaps people are convinced it's just a technical, enormous tour de force technically. In our case, we have to have nature help us, to have stars or whatever close enough so that we can see the effects which would come out of the spin and so forth. And that there, you can't go shopping. I mean, there is no other galactic center in that sense, okay? For the Event Horizon, people pretty much the same thing because if you want to go to more distant black holes, then you need a bit of bigger Earth to put the telescopes on. Not easily possible, although put them in space. And that has been proposed, but rejected, because that appears to be, interestingly enough, already beyond the current financial framework of ESA and NASA. And NASA. ESA has always been more modest than NASA, but on NASA. And that is frightening because that means we are, coming back to the beginning of your question, we are entering what I would call the zone of death, which the particle physics community have already experienced. That in principle, okay, if you build it 100 times more powerful accelerator than LHC, we probably see whatever. But we can't. It's just too expensive. And that could hit us in astronomy as well. So let's be not overly optimistic that we can do all of these things. But it doesn't stop me to try. I mean, it's just fun.
Okay, another question is the last question that I will ask for a gift. Black holes appears in a lot of movies, like Interstellar. What do you think of the representation of black holes in that movies?
I am fully convinced that our black holes, as important as they are, as I discussed, for our science, are just our movie stars. And we need movie stars to excite young people. I mean, there are parts of the sciences or medicine which undoubtedly are more relevant to people. But does that excite young people? I have seen here, I've seen elsewhere young people, even kids, 7-year-olds. I mean, here they were older and that's what we need. We need excitement in order to have people be willing to put the energy into this, because only that then allows us to make the next big step.
Okay, thank you. The last things I ask you is that in our National Institute we have a contest where kids of aged of 10 years, around 10 years, have to write a novel or a poetry, and this year's the theme was black holes. And then we will have the end of this contest in 2 weeks. Then I ask you if you can say something to these kids, okay, to encourage these kids to study, to develop a fantasy, and to study science.
So these movies will what would they have in them? Just sort of a.
No. These kids are writing.
They are writing.
They are writing novels.
I travel into the black hole, and
Yes,
I've hurt my foot in the last attempt.
Yeah. We had 500 of novels and the poetry, and then there are a lot of fantasies in the sense that some people are very scientific correctly, and then they developed a fantasy plot. And then the other described the direction of people on Earth if they look at one black hole arriving on the Earth, and the other they used the change in time in the sense, okay, it's a wormhole, I can look for the future, and then I saw that the Earth will destroyed in the sense of climate changes, and then looking at the future we can convince people here, convince kids to change something. What is interesting in these kids that they merging fantasy and science very well. And then if you can say something to these kids, to say to these kids, there are 500 kids, this is Concorso Rodari, sorry, just to encourage them to go further to study science. And
well, I mean, it's absolutely fantastic that you guys are already thinking about this at such an early stage. I didn't actually, and there's a lot of wonderful things to discover, really, and you know, not only what these things are and how they work, but also.
Just to say, I am Reinhard Genzel. Okay, just.
Okay, well.
Because they are very small kids, and then probably you have to present yourself, and then.
Okay, well.
Like you are speaking with that. Kids.
Okay, all right, get it. So, look, my name is Reinhard Genzel. I'm experimental astrophysicist, and I'm studying. What do you think? Black holes. Black holes, because we want to understand empirically whether these things exist and what properties they have. And you've studied black holes now. You've thought about them. Maybe you know more than I do. I don't understand them, but I find it fun. Maybe you should also study black holes. They're fun.
Thank you very much. Thank you. Okay, so the kids are fine. Thank you very much.